Hi, my darlings. Okay, so today we're going to take a little more time with differential equations. So what we're going to start with is we're going to write differential equations for different problem situations. We're going to get some practice with that first. So here's the first one. Water is being pumped continuously from a well at a rate proportional to the amount of water left in the well, where y is the amount of water left in the well at any time t. Okay, so now we know our variables are y and t. So now we're going to go back to the beginning, knowing that y is the amount of water. So water is being pumped continuously from a well at a rate. That means dy dt, that's the rate of change. Proportional to means equals k. The amount of water left in the well, that is y. There we go, dy dt equals ky. That's our differential equation, which, by the way, we know the solution is y equals y naught e to the kt. All right, let's try another one. An object moves along a straight line. Its speed s is inversely proportional to the square of the distance d the object traveled. Okay, so here we go. Its speed s, ds dt, is inversely proportional to equals k over the square of the distance. So we take the distance and we square it. There we go. All right, let's try another one. The volume of a sphere is increasing at a rate proportional to the reciprocal of its radius. So we're going to use V for volume and R for radius. That makes sense, right? Okay, so the volume of a sphere is increasing at a rate. So dV dt proportional to equals k, the reciprocal of its radius, so that's 1 over r, or just k over r. So dv dt equals k over r. Good. Now, the rate of cooling of an object is proportional to the temperature difference between the object and its environment. So y is the object's temperature, and a is the temperature of the environment. Okay? So the rate of cooling of an object, that's dy dt, is proportional to equals k, the temperature difference between the object and its environment. So we have a difference between the object and the environment. And there we go. dy dt equals k times the quantity a minus y. Awesome. Now, last one here. The rate of growth of the population of grasshoppers. Let's use P for population of grasshoppers is inversely proportional to the square root of the population. So here we go. The rate of growth of the population of grasshoppers, dP dt, is inversely proportional to equals k over the square root of the population, so the square root of p. There we go. dP dt equals k over the square root of p. Okay, so now we're going to do an old AP problem. This is from 1993. It's AB6. It's called the wolves problem. So let P of t represent the number of wolves in a population at time t years when t is greater than or equal to 0. The population P of t is increasing at a rate, so that's dP dt. That is directly proportional to, means equals k, and it's proportional to this quantity, so it's times 800 minus P of t, or I'm just going to write P to make our equation simpler here, and we're going to close. Okay, the P of t just means it's defined in terms of t. That's our independent variable. And they tell us that our constant of proportionality is the k. Awesome. So now in part A, they're telling us that P of 0 is 500. We want to find P of t in terms of t and k. That means those are going to be variables that we do not know. Okay, so what are we going to do? Let's start by writing our differential equation, dP dt equals k times 800 minus p. First step, get everything with a p to one side, everything with a t to the other side. And I'm going to keep my constant with the t's. So I'm going to have dp over 800 minus p equals k times dt. And we want to integrate both sides. However, we're going to need to do a u substitution here. If u is 800 minus p, then du dp, the derivative of 800 minus p is negative 1, so dp is going to be the negation of du. So now, when we make our substitution here, we have the integral of negative du over u equals the integral of k dt. Now we know that the antiderivative of 1 over u is the natural log of the absolute value of u, but don't forget to bring that negative down, equals the integral of k dt is kt plus some constant I'm going to call c1. Don't forget we need to do our substitution back, that this is the negative natural log of the absolute value of our u was 800 minus p equals kt plus constant 1. I'm going to divide out that negative, so I have the natural log of the absolute value of 800 minus p equals negative kt. Now negative 1 times c1, that's just a new constant, c2. Did you like that trick? Now we have a log equation, which in order to solve we have to change to an exponential. So we keep the absolute value of 800 minus p equals e was the base of the natural log, raised to the negative kt plus c2. Now we need to get rid of the absolute value, but in order to do that, we would have to show that the other side can be positive or negative. And when we have addition in the exponent, it means we used to have multiplication e to the negative kt times e to the c2. That's an e, not a c. There we go. Now we know that 800 minus p is this new constant. Positive or negative e to the c2 is just a new constant, which I'll call c3, e to the negative kt. Okay, so now we're going to take this back up here so we have space to work, and we're going to use this initial value that they told us. They told us that p of 0 is 500. So that means we can plug this in, because we have 800 minus p equals c sub 3 e to the negative kt. So this would be 800 minus p, and this initial value is 500, equals c sub 3 e raised to the negative k times 0 is 0. 800 minus 500 is 300, equals c sub 3, and e to the 0 is 1, so now we know c sub 3. Now we're going to take this and plug it into that equation, and we're going to have 800 minus p equals 300 e to the negative kt. We're almost done. Remember, we had to find p of t, so we need to solve in terms of p. So the first thing I'm going to do is I'm going to subtract 800, and I'm going to put it at the front so it doesn't accidentally become part of your exponent. Remember? You all tell me, oh no, I wouldn't, I know it's not part, and then it automatically, somehow, magically becomes part of the exponent. And besides, now I have to divide everything by a negative 1, and I have 800 minus 300 e to the negative kt. Now I have found p in terms of k and t. Whew, we have our equation. But of course, the problem's not done. So I'm going to rewrite that equation down here. P of t is 800 minus 300 e to the negative kt. Now they're telling us that if p of 2 is 700, we want to find k. So we're going to substitute in. So p is 700 equals 800 minus 300 e to the negative k times t is 2k, and we're going to subtract the 800 from both sides, so I have negative 100 equals negative 300 e to the negative 2k. Divide both sides by negative 300. I get 1/3 equals e to the negative 2k. I have an exponential equation that I need to change to a log to solve. So I take the natural log of 1/3 equals the exponent negative 2k. Now remember, when we have the natural log of 1/3, that's the natural log of 1 minus the natural log of 3, right? But we know that the natural log of 1 e to the 0 is 1. So all of that becomes negative natural log of 3. So we have negative natural log of 3 equals negative 2k. And yes, it's okay if you left the natural log of 1/3 in your answer. It's just a little neater if I don't have too many fractions and I want to review the log concepts with you. But yes, it's okay if you leave it with the natural log of 1/3. Now to finish off, we have to divide both sides by 2. So k is the natural log of 3 over 2. Phew, we found k. And we're still not done. Now they want us to find the limit as t heads to infinity of p of t. So we're going to find the limit as t heads to infinity of p of t. So that's the limit as t approaches infinity or grows without bound of, now what was our p function? Our p function was 800 minus 300 e to the negative, now we have to put in our k, so I'm going to put t natural log of 3 all over 2 in that exponent. Okay, now I want you to look at this. This part right here is an exponential function, right? It's a number times e raised to a negative number times x, right? It's a messy number, but that's what it is. That's exponential decay. That graph is going to go down and approach 0 as time goes on. So as time goes on, that entire part of the equation is going to approach 0. But 800 is never going to change. 800 is always 800, no matter what t is. So we have 800 minus 0 means that the limit is 800 wolves, which means as time goes on, the wolf population is going to level off to 800 wolves. It's what we call the carrying capacity. It's what the area or the region can support. It's the optimal number of wolves that the area can support. That's what it's going to level off to. All right, guys, have a wonderful day, and I'll see you soon. Bye.